Hi, everybody. Welcome back to our Let's CTF series. We have these on the third Thursday of every month. I'm glad that you've joined me once again. Last month, we took a look at a reverse engineering challenge where we identified how a file had been encoded so that we could get a flag out of it. This month, we're going to be taking a look at a packet capture challenge. This challenge was originally written, 6 years ago now, as part of the Army Cyber Institute's All-Army Cyber Stakes competition. And I am really proud of a lot of the work that me and my team at the time did for that competition. But some of these challenges are also really nice to reuse. We'll put a link to a write-up for this challenge and the challenge files down in the description on YouTube so that after this, if you want to go back, take a look at it, you can do that. And I'm kind of really excited to get into it with all of you. I'm going to start out with a little bit of a background on this challenge and why we kind of built it the way we did, why I designed it this way for the team to implement, and then we'll go into actually solving the challenge. Packet captures and kind of analysis of things flying over the network are pretty common both in the capture the flag world and also just in real life for forensics professionals or anyone kind of working with the network. Sometimes you'll be doing packet analysis if you're writing an application and you want to see how the different sides of your server client infrastructure are communicating with each other. So it's a very useful skill to have. It's a really kind of important thing to be able to do. In this case, we'd already written several kind of beginner packet capture challenges. We wanted something that was just one more step removed from look at the thing and get an obvious answer. So for this particular challenge, which is called a real packet in my cap, we have several different protocols flying over the network, lots of different kind of information, and multiple steps to solve the challenge. We don't just look at a single stream, a single website download and see what the flag is. We're going to have to jump through a couple of hoops to be able to find it, but nothing too difficult. All right. If you have any questions as I go along, you can always throw that in the comments on LinkedIn, the comments on YouTube, or over on Twitter. Those things will all get to me, but if you don't have any questions, that's fine. We'll just jump right into the challenge and we'll kind of walk through it as we go along. All right, so let's jump into my VM. I always tend to do things like this inside of a virtual machine because it's a lot easier to kind of contain the information and not have things outside of it. And that's the case when we're creating challenges as well. For this particular challenge, we do have a client-server infrastructure. We have two different things communicating with each other. And we have a packet capture that was taken only on one side of that. In order to do that, we actually did create two different virtual machines in an automated fashion because everyone who received this challenge got a different flag and a different kind of password to get to that flag. So the creation of this challenge was done in an automated way, and then we used TCP dump inside of one of those VMs to get the packet capture. It's a really interesting kind of process that we put together to automate the creation of this challenge, and I think that that's really useful and really interesting if you do have kind of a capture the flag that's set up with lots of different teams, and you don't want them to be able to kind of work together or share their answers. We use the Pico CTF platform to do that, and so we automated everything inside of Pico. It made the challenges and then served those to the individual contestants or players in kind of a Jeopardy-style environment. The creation of the challenge and of the VMs was all done kind of in an automated fashion, as I mentioned. And so I think that reusable infrastructure is a huge gain for anyone who does happen to be doing CTF development. If that's something you want to talk about, you can always reach out to me directly and talk about how we build some of these challenges or how we leverage some of those technologies to do it. Without further ado, let's go ahead and jump into this challenge and see kind of what it looks like. My first step is going to be to open the README over here because that has the instructions for the challenge. This was served via the Pico CTF platform when this was live. If we were to host this via something like CTFD, then we could use that as well. But because this is an already completed challenge, we're kind of over here in a VM, we just have a README file with the information. We also do have a set of hints here. All of our challenges come with hints, generally speaking, depending on the environment that we're in and whether we're creating them for a client who wants to have those or doesn't. I find them really helpful if people get stuck. Rather than have them as kind of unlockable here, all of them are just in one file. And so looking at those, we do know that there are going to be, oh, these are old. These are from last month even. Don't save. Don't save. There we go. So we can see here that we're going to have a packet capture with multiple communication streams. And there are more than one interesting stream in this PCAP. That's something that's different from a lot of, like I said, kind of introductory or beginner packet capture or network analysis challenges. We're going to have to go through a couple of different steps to solve this. So we're going to find one item of interest, but we're going to have to keep looking until we figure out what to do with that thing that we're finding. Now that we know a little bit about the challenge, which really just tells us a lot of information is here, we can look at the packet capture itself. And the most common way to do this is to load that up in a program called Wireshark. If you've been doing this for a long time, you might remember that it used to be called Peril, but that was before a lot of people's time. That was, gosh, decades ago at this point. Loading this up in Wireshark, we're going to see all of the different things that were captured by this one virtual machine as things were going over the network. So we can see things of different protocols. There's some SSH traffic here that we see. There's a bunch of TCP traffic. There's some DNS traffic. And then there are some things that are in TLS. Those are going to be encrypted in some way. One of the first things that I will typically do when I'm working on a project like this, when I have just a large packet capture with potentially multiple things going on, I want to see what might be interesting to look at first. And Wireshark actually has a way to do that. If you go up here to statistics, and then we choose protocol hierarchy, that's going to give us a window that just kind of tells us, here's all of the different protocols that are being used and the percentage of packets that are made up of that protocol. We can see that everything here is Ethernet. And that's to be expected. We're on an Ethernet network. We're capturing traffic from the Ethernet device. So everything is going to fall under that kind of Ethernet heading. We see that 98% of that is IPv4. Again, fairly normal. We expect that most of the things we're going to be interacting with are being sent over the IP protocol because we want to have some kind of like session awareness, or we want to be able to kind of send that information with a source and a destination IP address rather than dealing with our physical addresses. Inside of IPv6, we do also see some stuff, which tells us IPv6 was enabled on this device. There was some IPv6 traffic, but none of this really looks interesting. All of it is UDP, user datagram, and that has to do with, we could see name resolution and DNS. So we're going to go ahead and ignore this IPv6 stuff. It doesn't look like it's interesting. If it turns out we need to go back and look at it later, we'll know because we'll start seeing IPv6 traffic or IPv6 addresses, and we'll figure out that we need to resolve that. But to begin with, because it's only 0.5% and it's entirely around, almost entirely around looking at name resolution and IP address resolution, we're going to focus in on the subset of this that's sitting in IPv4. We could discount some of these things as a little bit less interesting in IPv4 as well. We have ARP here, Address Resolution Protocol. That's used to determine the IP address, the logical address of something, given a physical address, the MAC address or the EUI-48 address. So we probably don't need to worry about that too much because we are dealing with IPv4 packets here. So we'll see those logical addresses anyway, and we'll see with the associated Ethernet header what their physical addresses were. We don't necessarily need to look at the communication that happened to determine that. So we could discount that a little bit. A few things do jump out at me for the rest of this. We have some HTTP traffic here. So that is things like web traffic. We have a little bit of SSH that might be interesting. And then we have a lot of IRC traffic, Internet Relay Chat, that's also here. So it sounds like there's some kind of communication back and forth between two parties going on here. And there's also some things being downloaded or accessed or just surfed on the web. So those things could be really interesting for us as well. Generally, when we're talking application layer, we are going to be looking at things inside of the Transmission Control Protocol, TCP. That's what gives us that kind of multiplexing across multiple services hosted on a single IP address. That Transmission Control Protocol gives us 65,535 TCP addresses and 65,535 UDP addresses. Our UDP is going to be up here. We see, again, DNS, we see DHCP, we see some name resolution things. None of that seems particularly interesting to what we expect to see as far as like flags. It's absolutely possible that some of those protocols are being used to hide information. So while I'm saying initially I'm discounting those things, that doesn't mean that no CTF challenge will ever use them. And in fact, hiding information in other protocols is a fairly common thing to do for some of these forensic style challenges. But I'm going to come back to those things because they are such a small percentage of the traffic when we compare it to, the TCP traffic taking up 95.7%. So inside of this TCP, we're going to kind of focus in on those elements that look most interesting. We do have some TLS. 30% of our traffic is over TLS. That is things that are encrypted in transit. Those things are a little bit harder to look at because inside of our packet capture, that's encrypted data. We may not be able to decrypt that if we don't have the key material used to encrypt it. So I'm going to skip that for now. We can always come back to it if it turns out that that is important or is useful. Same thing with SSH. SSH, secure shell, is encrypted. And so, we can look at that 6.5% of our packets, but there's a good chance that in doing so, we're going to, not see a lot of detail, or we may kind of spend a lot of time on something that we can't get a ton of information from. So I'm going to focus in on some of these plain text things that we can look at the packets that were transmitted back and forth and see exactly what's inside of that. So that is a little bit of our kind of upfront decision making. I just took, 5 to 10 minutes to talk about just this protocol hierarchy screen here, but I think it's worth going through the process, the thought process that takes us to what we're going to do next. In an actual challenge, if I were trying to solve this whole thing would have taken me 30, 45 seconds, right? I would have looked at it, said, okay, discount this stuff. This isn't interesting. That's encrypted. ARP isn't going to be interesting initially. Let's focus in down here. But I wanted to kind of really walk through that decision-making process there. Oh, my VM fell asleep. So now that I know that I'm really interested in looking at this IRC traffic and I'm really interested in looking at this HTTP traffic, I can go ahead and close this window. I can come out here and I can make a decision about what I'm going to look at. Given that this is a CTF, I'm going to really, heavily focus on those communication platforms, or those mechanisms of, one side talking to the other. And so I'm going to immediately kind of focus in on that IRC traffic first. I'm going to come up here to my, apply a display filter in the top left, and I'm going to say that I am initially just going to look at this IRC traffic. So I do that, I hit enter. It's going to filter out all of the content to just those packets that are used for IRC. Now that I have that, I can see that, it's just this small selection of packets that are being used, and that a bunch of those are private message packets. That's a DM in IRC speak. If I take a look at this and follow that TCP stream, because IRC is a TCP protocol, I can see all of it kind of in one window. I can kind of go through each of them and try and figure out what it says by looking at this block in the bottom right. I can see, for example, that this first private message says, hey, did you get the file yet? But if I right-click on this, I can go to follow TCP stream, and that shows me the entire conversation color-coded at once. And that's a really nice way to say, what are they talking about? What is the information that they might have been passing back and forth? So if I look at this communication, this conversation, I see, hey, did you get the file yet? Nope, I'm grabbing it now. All right, got it. What was the key again? So we know that whatever they grabbed, there's some key or there's some kind of password to use it. That's going to be important information for us if we can also get that thing. So here, I'm going to take a look. I see this string here. That's probably the code or the key that they're sending back and forth to each other. I'm going to copy that. I'm going to copy that out into a, like a text file, just so that I can look at that later. So coming back over here into Notepad or whatever program you want to use, I'm going to copy that. I'm going to paste it. That is probably some kind of password to the thing that I'm grabbing. I also do know that they grabbed a file from somewhere, and that could have been a lot of things. So we know we have a key for the file, but we don't know what the file is that the key unlocks. So the next step is going to be to find that file of interest. Where do we want to look for that? Well, we know it's going to be, we know that they grabbed it. It says, nope, grabbing it now. So somewhere they're getting that file. It's possible that it was on a network file share. It's possible it was already on their computer, but that's unlikely because they said they didn't have it. So I'm going to go back to our protocols and I'm going to think, well, we saw a bunch of UDP traffic. We saw some ARP traffic. We kind of discounted those because those are more about like address resolution, kind of metadata for the networking, and not really going to be transmitting files. We also saw some SSH traffic, some SSL traffic. Both of those could be used to download a file. SCP, secure copy, operates over SSH. So it's absolutely possible that they used SSH to download that. We also saw some SSL traffic. It could be that they went to a TLS-enabled website to download it. Both of those, like I said earlier, would be harder for us to tear apart. And this, we do know, is on the beginner side, the kind of low point value challenge, so they're probably not going to make us break cryptography. It's possible, and if this were a harder challenge, maybe we'd start looking there. But my instinct, the only one worth investigating for a file out of all of those protocols we've seen is our hypertext transfer protocol, the HTTP traffic. So I'm going to go ahead and come back in here. I've gotten everything I can out of this. I'll go ahead and close that. And now, instead of looking at my stream of 25, which represents my IRC traffic, I'm going to change my filter over to HTTP, hypertext transfer protocol. Again, by doing that, hitting enter, it's now going to filter all of that to just the things that are HTTP traffic. And we can see that there's really only one request here. We saw a good amount of HTTP traffic in size in packet content, but when we look here, there's actually only 4 packets that represent this. And we can see that they're doing a get first for the root of something, for slash, which resolves, and then there is a get here for /deaddrop. That is significantly longer. We can see that that's 520 bytes versus kind of the rest of it. So that might be a file, it might be something else. I'm going to go ahead and look at this filter, and we can see that they are kind of downloading that. And inside of this, here's their user agent, here's the headers that they're doing, some refer headers. If I kind of open this up, take a look at the raw data here, we can see that there is, here we go, a gzip or deflate encoded thing. Here's the full request. And then the response, if we take a look at that response frame down here, has a whole bunch of file data in it. That could be a lot of things. We don't know exactly what it is, but we do know that they were getting a page and that this is returning something. And inside of that data is a whole bunch of information here. One of the first things that I'm going to notice is that it starts with ELF. So that's probably a Linux executable. It's an ELF file. It's possible it just has that at the beginning of it, but those magic bytes at the beginning of a file typically are going to represent an executable. So they're probably downloading some kind of executable in this. And based on some of the other information here and kind of my own knowledge, it's a 64-bit binary just by some of the magic numbers here. We could try to export it from this window that we have here, but that's actually a lot more work, because one of the nice things that Wireshark will give us is that if we go here, we can go to File. We can go to, let's see, where did we put it? Export Objects. And we can see here that we can grab that HTTP object. And that's just going to be the data, not any of the headers. So here is kind of the first part of it. And then here's the deaddrop file that was being requested as a part of that HTTP. I'm going to go ahead and save that. So now that I have grabbed this, save it, that's going to give me a file called deaddrop. And I'll just go ahead and put that back in the same folder I'm working on. If I go into that folder, then I now have that file. So from this packet capture, so far, we've identified an IRC packet or an IRC communication that, among other things, gave us a password. And then we saw that they also downloaded deaddrop. If I go back into the packet capture, if I go back into the timestamps, I can see when those things happen, and I can correlate the grabbing it now and the time that this was downloaded to each other and see that this is the file that they were talking about. As a CTF challenge, I probably don't need to do that because it's a contrived environment. But if I was doing timelining, if I was doing true forensics, if I was actually in a DFIR environment, then I would do that. Because going through and identifying when things are occurring and how they relate to each other is a big part of identifying things inside of incident response as we're doing that kind of forensic analysis. Now that I have this, I do know it's an ELF file. And I'm on a Windows system right now that's not necessarily going to be useful. At this point, I would boot into Linux or bring up WSL, and I would run this file that way. Another way to do it, though, is that I'm just going to open this up inside of my decompile or disassembly program. So I'm going to use IDA once again. This gives us a little bit of that kind of reverse engineering as we saw in the challenge last month, We could also have just ran this thing or run strings on this thing to kind of see more information kind of from a static perspective. But because I'm interested in kind of showing some of the different pieces of this, let's go ahead and throw it into IDA-Pro. Again, if all we were doing was a forensics challenge or forensics analysis, and we didn't want to show off some of these pieces, you don't need IDA or Binary Ninja or Gehidra to solve this challenge. But I think that it's interesting to look at it. So let's go ahead and do that. Okay. So here we see the main function, and we can see that we have kind of a couple of different paths that we have here. The first thing it's going to do is, check to see, is there an argument that is called drop? And if we don't have arguments, then we're going to go down an error path. We have an error path here. So we know that there is something that's looking for drop from that string compare. And then similarly, we have something down here that's doing a string compare for pickup. I know that I'm doing this kind of quickly, I'm running through it, but this is often what we'll end up doing once we have a little bit more experience looking at this disassembly. We also have a function call here to something called doDrop, and that's what's going to occur if we had this drop call. There we go. So if we're putting an argument on the command line that is drop, it's going to call doDrop. And then we have something down here that's comparing to pickup, and then we have a call down here for doPickup. So we really see that there are two options or two paths that we could go down just from the kind of basic execution of this program. We can also take a look at our strings view like we did last month. So if you go to View, Open Subviews, Strings, there are some interesting things in here that will tell us some of the same things that we just saw from taking a look at that the content over in the disassembly. We know that we have something here that's going to looks like a format string. It's plain text %s. And that is saying we're going to print out something in the format of a string using something like the printf function in C. We also have key and IV. That tells me that we have some kind of cryptography going on here. And we'll take a look at what that looks like in a second as well. But we know that there is starting decryption. We know that we have a file name, could not find ciphertext. We know that there's some kind of encryption and decryption happening as a part of this. And it looks like, based on the fact that we have a drop and a pickup, based on the fact that we have our keys or IVs, a starting decryption here, ciphertext, that this probably is a program that does both the encryption and the decryption based on which of those two paths that we take. Going back into our IDA view, we can kind of pull this back. We can look at these calls, or if I hit my minus key, that gives me my proximity view. This is like a call graph. So we can see that we have main calls doDrop, we have doPickup, and we can expand that a little bit to take a look at what else we've got going on. Or if we go back to our main, let's see where we got it. We also see over here in our function list some AES calls. We have AES init context, init RIV. So we're using some kind of AES encryption somewhere. If we jump back to, let's see over here, where did I lose my main? If we jump back to main and we look at some of these calls, for example, our doDrop call, we can see that we are calling these AES encryption functions. We're encrypting a buffer here. So we have encrypt buffer, and then if we go to doPickup, we expect to see the opposite. We're probably going to see something in here calling decrypt buffer. And it's important to do this kind of analysis because, just because something is called drop and something is called pickup doesn't mean it does what we inherently think it does from those function names, because we could name those things whatever we want. The good news is, because this is an ELF, a Linux executable, we do have a lot of symbol information still available for us. So those function names like AES CBC decrypt buffer are there for us. If we had a stripped ELF, or if we had a portable executable, the Windows format, we wouldn't have symbol names. It would just be sub underscore something or other. Like I said, though, we do have these raw strings that say pickup and drop. So even if we didn't throw this into our disassembly, even if we just looked at this on the command line using something like the strings utility, we could still see that those are arguments, or those are strings at least, that are expected somewhere. So my next step would be to run this inside of some kind of environment where we have access to it. So I'm going to jump down and see, do I have WSL installed? Do I have bash here? it looks like maybe I did not install that on this system, which is unfortunate. Clearly, I didn't prepare enough for today's demo, but we do know what those arguments were. And so using the key that we had, we can pass that in either from the command line or write our own implementation that uses that string. So my first instinct here would be to open up something, again, that can run an ELF, and unfortunately I don't have that on this system. I need to boot another VM, but I can do that. Let me come up to my VMs. All right, bear with me while I do this. And I'm going to switch over to my Ubuntu VM, which will need a second to boot while that's booting. So far, we've taken a look at our packet capture, and we've been able to kind of analyze it to see we have streams in it of two different protocols that are interesting and useful to us. One of them was IRC. And from that IRC communication, from that conversation that two people were having, that two sides of our analysis were having, we were able to determine that there is a password being transmitted here. And that password that's being transmitted is used, now we know, as the key material for an AES CBC cipher. So now we can encrypt or decrypt using that password that we had. We also found the executable that did that. It took in the password and it did some kind of drop using that. It either created a file, if we were to drop it, or if we're trying to pick that up, will give us that value back. So now we're going to go over to our Linux VM, which is still booting for some reason, and run that executable. That executable will allow us to, hopefully, assuming that we understood it quickly, from our quick analysis, get that flag right back out. Bear with me. Oh, there we go. Boot to Ubuntu. All right, I got as far as my grub menu, so that's something. Let's go back over here. There we go. As Ubuntu boots. Okay. Oh, live demos always have their hiccups, so hopefully this resolves quickly. I apologize for the brief thing there. As that does continue to boot, hopefully we can watch that happen. The techniques that we've looked at over here on the Windows side, particularly inside of WireDark, these are things that we're going to be using quite a lot for any kind of packet capture analysis. And these filters that we're doing up here, that's kind of the bread and butter of packet analysis. Being able to take a look at this environment and say, what is interesting in it? Where do we want to focus? And how do we focus in on that? And something to be aware of in here is that these are these can be compound filters. So if I wanted to say, for example, it could be HTTP or IRC, I could do that. I can give it this kind of pipe, and now we can see that we have the IRC traffic and the HTTP traffic, which gives us that answer of, that timeline we were talking about earlier. Nope, grabbing it now is this packet here. Oops, there we go, this packet here. Then we immediately see that HTTP GET, that set of requests where first they're getting the root, and then they're downloading dead drop, and then we have the rest of that IRC conversation. So that allows us to do that timelining really easily by just filtering to just those packets that we're interested in at that point. Goodness, this is taking forever to boot. Okay, well, I guarantee you that were we to run that inside of there, we would see that flag pop out. And rather than hold you here while my VM takes forever to boot, oh, nope, there it goes, maybe? Here we go, okay. Let me go ahead and grab that dead drop file. Copy link. So I'm just going to grab a terminal, and I'm going to download that file. In this case, I'm actually grabbing it from the write-up that somebody who was in the competition wrote. They were nice enough to also upload the file that they got. So I'm just going to grab that dead drop. If I look here, I have dead drop. So I'm going to make that executable, user plus x, dead drop. Now that it's executable, I can run it. And that would give us something. Now, we know in this case, going back to our kind of analysis over here, that we want to run it, and we want to run it with arguments. We know that we want to use the pickup argument because when we were looking at that in IDA, we had a couple of options, right? We had drop and we had pickup. We know we want to use pickup. We don't know exactly what arguments that we need for that. So if we go into do pickup, we can see that as arguments, it is looking for 2 of them and is using that to start the decryption. Then it has like the IV and the key. We know that we have that key over here in this file. So I'm going to use that. I'm going to copy it out to another place. Let's see. And then over here, remind me later. There we go. I'm going to run dead drop. I'm going to run that with the pickup argument. And then I'm going to grab that key. All right, so we got a result out, but it's not a result that is useful for us. And that probably tells us that what we copied out has more or less information than expected. So I'm going to delete that colon. There we go. It looks like that colon was not part of the key. It was just part of the message showing it to us. And when we print that out, we get our key for the Army Cyber Institute CTF, the All Army Cyber Stakes. And that is the key value we would then go and put back into our Pico CTF environment to get credit for this particular challenge. So we did it. We had a little bit of a hiccup where I needed to boot over to an Ubuntu VM. Sorry for the brief block there. But overall, I think that this was a pretty successful walkthrough for a fairly straightforward problem. Again, I did go with my instinct of throw this in a disassembler and see what happens. We could also take a look at decompilation over there and said, you know, what is this doing in C pseudocode? We see that it is taking in a string here, and it's using that string as the key. So if we go up 1 layer, again, looking at C pseudocode in the decompiler, we can see that it is looking for 2 arguments here. argc has to be 2, so we saw that one of those was pickup. argv1 should be pickup, and then argv2, oh, there we go, helps if I have the right screen up. In my decompiler, we can see that when we're calling for pickup, we're looking at argv1 needs to be pickup, and then argc needs to be 2. argv2, that second command line argument, needs to be the thing that is then used inside of this do pickup function. If we take a look at its decompilation, then we can see that argument up here, which is just a string, constant character star A1. A1 is being used down here to initialize that IV. So it's going to be that key material. Exactly what we saw then happen over in our Ubuntu VM. We see that we are able to decrypt using that key. It used a static IV that is all Bs, and it gives us our plain text string. I hope this was useful for you. I hope you enjoyed it. Join us again next month, 3rd Thursday of the month, where we'll be taking a look at another CTF challenge. If you have any particular category of challenge or anything that you're interested in taking a look at, feel free to reach out, and I will prioritize that sort of thing. Otherwise, I'll pick something between now and then, and you'll see quite a bit about it once we dive in. Thank you for joining me. I know that this one is about half the length of last month's. We got a lot of feedback that an hour is a little bit of time to be spending. So hopefully this half-hour challenge was a little bit easier. Thank you all, and I'll see you next month.